All right, I apologize for the double video. Baby was moving, and I was also trying to figure out the output values here, but I think I've got it now. So we basically have to deal with the inputs. These output values that they gave us here, they were actually given. So we don't need to worry about the output values. We're just going to worry about the input values, okay? So these were basically the y's, okay? And these over here are the x values for the graph. So basically it's saying to complete the mapping diagram, to go from G to F, we subtract 2. And that's what the instruction told us right here, okay? The other interesting thing to point out is that notice this function that they gave us was h was negative, but the h they gave us was positive. So when we went into these parentheses, it actually flipped. It was actually acted as if it flipped signs, okay? So to go from G to F, we subtract 2. So 1 minus 2 is negative 1. 3 minus 2 is 1. In order to go the opposite direction, because they gave us the blank boxes, so in order to go back that way, we would add 2. So 3 plus 2 is 5, and 5 plus 2 is 7. Okay? And then we're going to go ahead and graph that on here. We're going to use these x values and these y values to get our g graph. And notice the y values were the same on both the f and the g. All right, so we're going to go out 1, down 2 for our first point. Then we're going to go out 3, up 2. And then we're going to go out 5 and down 2. And then we are going to go out 7 and up 2. So you'll notice that our graph ended up going to the right this time, okay? It translated the number of units that we said, but notice inside here it's deceiving. It looks like it should be left because it's negative. So it's the opposite sign when it's inside the parentheses. All right, so let's answer our question. In general, how is the graph of g of x equals f of x minus h related to the graph of f of x when h is a positive number? So we would say when h is a positive number, h is positive, g of x equals f of x minus h translates to the right, h units. Okay. All right, so they're going to ask us to make a little bit of a conjecture. How would you expect the graph of g of x equals f of x minus h to be related to the graph of x when we have a negative number? Well, like we saw in our first part of the Explore, it had an opposite effect when we changed the sign. So if it goes, when it's positive, if it goes to the right, if it's negative, it should translate the other direction. It should translate to the f. So we're going to write that out. When h is a negative number, g of x equals f of x minus h, it translates to the left. All right, so now we're going to reflect on this a bit. Okay. Suppose the function of f has a domain of x sub 1 to x sub 2 and a range of y sub 1 to y sub 2. So now they're making us make it generalizations without numbers in it. When the graph of f of x is translated vertically k units, where k is either positive or negative, how do the domain and the range change? So if we're going to go vertically k units, the domain is, so let's look at one that went vertically. Let's go back to that. Okay. So when we went vertically here in this first example, did our x value of our domain change? Doesn't appear. It looks like it started at -1 and ended at +5 on both of them. So a vertical translation doesn't seem to have any effect on the domain. So let's write that down. So domain is the same. Okay, let's go back and look at the range now for the y values. You'll notice, let me use a different color. Use red. Okay, so our y values were here to here. Now they're here to here. So you'll notice the y value, the range value actually changed. And it changed, look, 1, 2, 3, 4. It changed by 4 units, which was what we were adding here. So let's write that down. Oops, too far. So the range changes. And I'm going to show you the fancy math way to write this. So it changes from what we had, the y sub 1, y sub 2. And basically what we did was we added the k to it, right? So we're going to say 2, and the fancy math way to write it would be y sub 1 plus k, comma, y sub 2 plus k. So basically that's saying that it moved it up k units. You could write that down as well. All right, so now suppose a function f of x has the domain and range, the same domain and range. When the graph of f of x is translated horizontally, where it's either positive or negative, how do the domain and the range change? Okay. So the domain and the range, so again, this time we're going horizontally. We notice that the range changed when we did that vertical. So probably when we do the horizontal change, the domain is going to change. So let's look at this one here. Here was our horizontal change. So looking at the range values, those didn't change. The y values didn't. It's still going from the same bottom one to the same top one. But here's the domain values. There's the x's there. There's the x's there. So it changed, and again, it changed by that distance that we went, which in this case was an h. Okay, so it changed h units. All right, and I'm not gonna write it fancy. I'm gonna write it in words. Okay, for this time. So the domain changed by h units. Range is the same. All right, you can transform the graph of f to obtain the graph of g of x equals f of x minus h plus k by combining transformations. Predict what will happen by completing the table. Okay, so they're saying if h is positive, so remember that's going to make the sign opposite, so it's going to keep it negative. A negative change, or that makes it go, well, a sign of h as positive is going to make it move to the right. So we're going to use that fancy word translate. Right h. And the negative is going to make it, because if positive makes it go up, negative has to make it go down, and down k units. Okay. All right. A negative h, which means that sign is going to actually change to a plus sign when we would see that in there. So if a positive sign makes it go right, a negative sign must make it go left. So we're going to use the fancy word translate again. Translate left h, and when it's positive here, we know that that's affecting the y value, so it goes up k units. And then we have a negative h, so again, that's a translate left. Left h. And a negative makes it, in k, makes it go down k units. All right, so we're going to do explore 2. I think there's 3 explorers today, so that's why we're only doing explorers today. All right, so in this activity, you'll consider what happens when you multiply by a positive parameter inside or outside of a function. Throughout, you'll use the same function f of x used in the previous activity. So first graph a times f of x, where a is a parameter, let a equal 2. So basically we're taking our function, we're multiplying it by 2. We're supposed to complete the table, then we'll make our generalization. So all we did was multiply by 2. So negative 2 times 2 is negative 4. 2 times 2 is 4. 2 times negative 2 is negative 4. And 2 times 2 is 4. So we're going to graph these x's with these y's. So I'm going to start by going negative 1, negative 4. 1, 4. 3, negative 4. And 5, 4. And you'll notice it has the same basic shape, but it looks like it was pulled, and stretched is the word we typically use for this. So we're going to say that it's not just, it looks like it's stretched vertically. This looks like we pulled it up and down. So when a is, oops, let's see what kind of parameter do we have? We said we had a positive number, right? So when a is, actually we're going to say something different. We're not going to say that it's positive. We're going to say that it's greater than 1, because if I had just a 1, it would have left those numbers the same. So when a is greater than 1, g of x equals a times f of x, that's an a, is stretched vertically. Okay, now it wants us to do a value that's between 0 and 1. So we're going to do let a equal 1/2 this time, okay? So we're going to multiply everything by 1/2. So same function, multiplying by 1/2. So we're going to multiply by 1/2. These 2's cancel, I get negative 1. Multiply by 1/2, 2's cancel, I get 1. Multiply by 1/2, 2's cancel, I get negative 1. Multiply by 1/2, 2's cancel, I get 1. All right, so we're going to plot these x's with these y's. So we have negative 1, negative 1, 1, 1, 3, negative 1, and 5, 1. So notice it looks like it got squished this time. So the fancy word for squishing is that it's compressed vertically. So when a is between 0 and 1 was our parameter. So notice we said it had to be between, oops, sorry, flipped. Between 0 and 1. It doesn't like it when I touch the top. So between 0 and 1, that's where we got this, and this is the fancy way to write that domain. Okay, so when a is between 0 and 1, g of x equals a times f of x is compressed vertically. All right, we're going to go back to kind of the other crazy mapping diagram, okay? If you like the boxes and the tables, you can use that. They happen to use this mapping thing on a few of these. All right, so the difference here is that this was on the outside of the function. Now notice they're putting it on the inside of the function here, okay? So this is going to change it a little bit differently. So now the graph g of x equals f times 1 over b times x, where b is the parameter. So we're going to let b equal 2. So notice it's multiplied on the inside. Complete the mapping diagram, then graph g. To complete the mapping diagram, you need to find the inputs for g that produce the inputs after multiplying by 1/2. So if I multiply these inputs by 1/2, I get 1/2, negative 2 times 1/2 is negative 1. 2 times 1/2 is 1. In order to go backwards, it says that we need to multiply by 2. So in order to go back this way, I'm going to multiply by 2. So 3 times 2 is 6, and 5 times 2 is 10. Again, we're not touching the outputs. They were given to us, okay? So we're going to graph it with these inputs and these outputs. So these x values and these y values. So -2, -2. And then 2, 2. And then 6, -2. And then 10, 2. And you notice when we connect our dots this time, it looks like we pulled it left to right. So it looks like we did a horizontal stretch on it. So, and that again, it looks like when the b value on this one is greater than 1 again, was what we had. Okay, so we'll write that down. So when b is greater than 1, g of x equals f of 1 over b times x has a horizontal stretch. Okay. All right, let's see what that make a conjecture says here. So how would you expect the graph to be related when b is a number between 0 and 1? So let's think about it. It's got to be opposite, right? Because it was opposite last time. So if it's between 0 and 1, it's likely to be compressed, just like the other one was compressed. So we would say when b is between 0 and 1, the graph, or f g of x equals f times 1 over b times x is compressed vertically. Not vertically, I said it wrong. Horizontally. Okay. All right, so we're going to do some reflecting here and kind of summarize what we've done so far. So suppose the function f of x has a domain and a range when the graph of f of x is stretched or compressed vertically by a factor of a. How do the domain and the range change? Okay. So let's go back and look at it. So it says it was stretched or compressed vertically. So let's go back to our vertical ones. Here with the vertical ones. We change colors. So you know we're looking at domain. Domain doesn't look like it changed on that one. Domain does not look like it changed, so it doesn't look like it has any effect on the domain. So we would say, oh, what about the range? Domain is the same. Domain is same. All right, so now we need to examine the range. So let's see what happened to the range on those. All right, so it looks like the range, it went from -4, and it was at 2, -2, and to 4. So it looks like, if I was looking at the range, it looks like when I go from -2 to -4 and 2 to 4, it looks like we're multiplying that by 2, which was what our a value happened to be. Let's see if that works for the compression too. It looks like we went from -2 to -1 on this piece of the range, and then this one went from 2 to 1. So let's see, our a was 1/2. So if I multiply by 1/2, did that work? It looks like we multiply by the a value. All right, so the range changes. I'm going to use the fancy math notation from y sub 1, y sub 2, oops, sorry, bracket 2. And it looks like I multiplied by the a value, a y sub 1, a y sub 2. All right, you can transform the graph of f of x to obtain this. This is the general form of that function. So we're going to combine transformations, predict what will happen by completing the table. So we learned as we were going through the little explore, so this is summarizing our explore, and when a was greater than 1, we stretched vertically, okay? It's going to still translate h units horizontally, k units vertically. That's what the h and the k do, is the translations, which is what we learned in the first explore. So the big difference here is that it's going to compress vertically because we're between 0 and 1. So compress vertically by factor of A. And we're going to still translate H horizontal and K vertical. All right, you can transform to obtain this by combining transformations, predict what will happen. Okay, so when we do the B value on the inside, it's a horizontal stretch. We still translate H horizontal, K vertically. When it's between 0 and 1, we know it's a horizontal compression. So compress horizontally. By factor of B. Oops, sorry. Translate H horizontal and K vertical. Okay, last explore, and then we'll get you going on some assignments here. So when the parameter in a stretch or compression is negative, another transformation called a reflection is introduced. So we need to know when the parameter is negative, we have a reflection. Examining reflections will also tell you whether the function is even or odd. So let's underline here. An even function is one for which f of negative x equals f of x for all x in the domain. An odd function is one for which when we put a negative in, we get a negative of the function. Function is not necessarily even or odd. It could be neither. So it could also be neither even or odd, which seems weird, but it does happen. So first we have this graph where a is -1. Complete the input in the output table. So basically all I'm doing is multiplying this by -1. So we're basically going to swap our signs. So we're going to have 2 multiplied by -1. We end up with -2. Let's go ahead and plot these x values and these y values. So we've got -1, +2, 1, -2, 3, 2, and 5, -2. I should have used a slightly different color. Okay, so hopefully you can tell what's blue and what's black. See if I can highlight that. All right, that's a little bit better. Okay, so, oops. Okay, you'll notice what happened was it looks like it kind of folded on this line. So what was down here ended up going up, and what was up here ended up coming down. So that's a reflection, as if you're looking in the mirror and you see your reflection. It was mirrored across that line, the x-axis. Okay. So in general, how is the graph related to the graph of g of x related to the graph of f of x? It's a reflection of it. So g of x is a reflection of f of x. Should call it g of x equals -f of x. All right. Now they're putting the negative underneath. Complete the input and output table. So basically I am multiplying by -1 to go this direction, which means I'm dividing by -1 to go the other direction, which is really the same as multiplying. So when I do 3 divided by -1, I would get -3. And 5 divided by -1, I would get -5. So we're going to use these those x values and these y values. So we've got 1, -2. We've got -1, 2. We've got -3 and -2. And we've got -5 and 2. So here is our graph. And hopefully you've noticed that we have a reflection. I'm sorry, what happened there? We have a reflection. It's just a different one. it's now reflecting across that y-axis. So so how are they related? It's a reflection in the y-axis. So g of x equals, so when the negatives on the inside I reflect on the y-axis, is a reflection of f of x in the y-axis, or across the y-axis. All right, so let's reflect on that just a little bit, and then that's going to be it for today. So suppose a function f has the domain of x sub 1, x sub 2, and a range of y sub 1, y sub 2, and the graph is reflected across x-axis. How did the domain and the range change? Got it. So did our domain change? Doesn't look like it. Did our range change? Doesn't look like it. So there was no effect on domain and range. No change in domain or range. For a function f of x, suppose f of negative x, the reflection of the graph across the y-axis is identical to the graph. What does this tell you about f of x? Okay, so let's go back and look at that even and odd stuff. So if we got the exact same picture, okay, so it's saying that we had a reflection. It said it was f of negative x, which is right here. If it comes back to the original function, that means that you had an even function. So if your pictures looked exactly the same, it would be even. So we would want to say that because B slash C is because f of negative x equals f of x is an even function. All right, is the function whose graph you reflected across the axes in steps A and B an even function or an odd function or neither? Okay, so if I look at this, an even function should look like itself, okay? An odd function should look like the negative of the function, basically. So it should be the same y values, but negative of them. So basically, the even function, we know that it's not it wasn't an even function because it didn't land back on itself when we did these steps here, okay? If it was an odd function, we would have gotten the negatives, we would have gotten opposite outputs here, and we didn't. We got the same outputs. So it's also not an odd function, so it's actually neither in this case. So we'd say that it's neither because step B isn't identical to the graph of f. Not identical to graph of f of x, and step A not identical to the graph of f of negative x. Sorry. Yep, no, it's negative on the outside, negative f of x. All right, that's it for today. So go ahead and look at what the posted assignment is.